Okay, so let me begin by welcoming everybody. This is the Spring 2021 Nonlinear Analysis Seminar Series. And today it's my great pleasure to introduce our speaker. Our speaker is Professor Giovanni Leone, who is my advisor. And so I'm particularly happy to host you today, Giovanni. Giovanni will be speaking about some remarks on homogeneous fractional subwell spaces. So without further ado, welcome.
Thank you. Thank you for the invitation. Yeah, so I'm going to talk about homogeneous subwell spaces and homogeneous fractional subwell spaces. So let me start with the homogeneous subwell spaces without fractional. And I'm going to define them, and then I'll mention a few instances in which to explain why they are important. And so the main, so let's take an open set in Rn, and let's take p between 1 and less than infinity. And then we say that if I take a function u, which is, it's not in LP, it's just locally integrable. So it's, let's say, in LP loc. We say that u belongs to the fractional subwell space. So sorry, to the homogeneous subwell space W. I'll put a dot to indicate homogeneous, so W1P of omega, if the weak derivatives are in LP. So the gradient of u, it's in LP of omega with values in Rn. And so the main difference with the standard subwell spaces is that you don't require the function to be in LP, it's just integrable on compact set. And so why? So why do we want to study this type of spaces? Or why not the classical, the standard W1P spaces? And I'm going to give you two main motivations. The first one is like if you have an unbounded domain, so if omega is unbounded, and you're working with the PDE, so then in unbounded domains, usually the classical subspaces are not, they don't work that well. So let me give you a very simple example. So let's take omega to be the complement of the unit ball. So let's take Rn, and then let's remove the unit ball. And then let's take the Poisson, Dirichlet problem. So let's take the Laplacian of u equal to 0. So we're looking for harmonic functions in omega. And let's put Dirichlet boundary conditions, so u equal to 0 on the boundary of omega. And then what you can prove is that if you take the fundamental solution, so say, let's do, I don't know, in the case n equal 2, so in 2 dimension, if I take u of x, which is just, say, the log of x, so this it's a harmonic function, and it solves this Dirichlet problem. Or if you are in, say, in dimension bigger than 2, so n bigger or equal than 2, you can take u of x, you just take u minus the norm of x to the 2 minus n. And so you have these solutions of this homogeneous, of this Dirichlet problem, and you can check, I mean, one is the log, and the other one is a power of x, 1 minus the power. So this function, they're not in any LQ. So this, it's not in any LQ of omega for any q. Any q between 1 and infinity, or less or equal than infinity. But if you take the gradient, and even more if you take the Hessian. So the second derivative of u is going to be in LP for every p, for p between 1 and infinity. And so you have a solution of like a very simple partial differential equations in an unbounded domain, which is not in, say, in W2P. So this is the typical situation when, so say, the function u, it's let's look at, for example, the gradient is in the homogeneous Sobolev space W1P, values in Rn. But it's not, and in general, it's not in W1P, okay? And so this is one application. So like you have the gradient, you have solution of PD, which are not in the standard Sobolev space W1P or W2P. The other reason why we want to study, in general, we study homogeneous Sobolev spaces is when omega is not regular. So so this, I could say example 1 and example 2, say omega irregular. And so here there's a very famous example which is due to Frankel, and is like, this is called room and corridors. So rooms and corridors. And so what you do, you take a room, which is just, it's a square in R2, and then you join the room. So this is the room. And then you put a very narrow corridor. Then you take a smaller room, and then you take a smaller, a narrow corridor, and then you keep doing it. So you do rooms, corridors, and eventually you're going to stop. You're going to stop here. And then what you can do is that you can construct a function. So you can construct a function u, and the way you're going to do it is going to be constant. U is going to be a constant. So c, so constant in each room. And then in the corridors, you're just joining the two constants. So if here I put the constant C1, here I put the constant C2, here you just take any affine line which is joining C1 to C2. And so what happens that in each room, the gradient is going to be 0 because you are constant. So the gradient is equal to 0 in the room. And so what you can prove is that in this situation, the gradient of u is say, you can construct function for which the gradient is in L2, but the function itself, it's not, because if you take the constant, the sequence of constants C1 and C2 large, you're able to prove that u, it's not in L2. And so again, this is a situation in which you are in the homogeneous Sobolev space, but you're not in the classical Sobolev space. So you're say in W.12, but you're not in W12. Okay, so these are just two examples of why we care about homogeneous Sobolev spaces. Okay, so now the type of results that we're going to discuss are density type of results. So we want to discuss density in homogeneous Sobolev spaces. And I'll just consider the simple case in which we are in Rn. And so there's a paper, I think from 95 of, so 1995. So this is Ajalax from Pittsburgh. And Kalamashka, I don't know how to pronounce it. In which they prove the following density result. They do it for any type of any number of derivatives. I'm just going to give it in for one derivative because so the theorem is the following. You take p between 1 and infinity, and you take a function u in the homogeneous sober space W1p. All right. And then what they were able to prove is that they can construct a sequence. Then there is a sequence of functions. So you find the function un, which is C infinity. It has compact support, so it's a smooth function with compact support. And it converges to the function u. In what sense? Only with respect to the semi-norms. So the gradient of un minus the gradient of u in LP goes to 0. Okay, so as I said, u in general is not in LP, and so you only have this result. And what they were able to prove this is that you have this sequence. You can go say so if and only if. So it's a full characterization. Either P it's strictly bigger than 1. So well, let me write this. Either you are in dimension bigger or equal than 2, or your P is bigger than 1. So it fails in dimension 1 and when P is equal to 1. But in all the other cases, you do have this density result. Okay, so now why do we care about this type of results? Like let me give you a simple corollary of this type of density. So as a corollary of this, you could prove, let's go into the subcritical case. So let's assume that P is less than the dimension. And let's take a function u in the homogeneous sober space W1p over n. And then you can prove a version of the Sobolev-Gallardo-Nirenberg inequality. So what you can prove is that there exists a constant, then there is a constant which depends on u. So let me see, it depends on the function u, such that if I do, I take u, I subtract the constant, and what I get a function in the in LP star, in the critical sober space. So this is bounded by a constant times the gradient of u in LP. And so in this subcritical case, you can prove that if I take any function in the homogeneous space up to a constant, it's in LP star. And so you get Sobolev-Gallardo-Nirenberg in the homogeneous sober space. Okay. So this is what has been done for the case when, as I said, k is equal to 1. And also you can do the same for k when k is an integer. So you can do higher derivatives. If you consider wkp, so if you have derivative up to order k, here the difference that instead of a constant, you're going to get a polynomial of degree k minus 1. Okay, so now we come to what I did. So what I was interested was in extending these two results, so the theorem, this density theorem, and then this corollary, to the fractional sober space. So let me give you the definition. And so let me take S between 0 and 1. Let's take any P between 1 and infinity. Let's take an open set. And so we say that a function u, again, I'm going to take it in LP lock. So it's not in LP of the entire space, but if I know a compact set, it behaves well. So u belongs to the fractional sober space the homogeneous fractional Sobolev space so it's W dot SP of omega if the following semi-norm is finite. So the UWSP of omega. So here you take, it's the integral of omega, the integral of omega, and then you do U of x minus U of y raised to the power p, divide by the norm of x minus y, and plus sp. Integrating the x, integrating the y, and then you raise to the power 1 over p. And so you want these semi-norms to be finite. And of course, the non-homogeneous case is that when U is in LP. Okay, so this is the equivalent of the homogeneous Sobolev space W1P. Okay, so the theorems, I'll give you the theorems which corresponds to the theorem, this theorem here, and then I give you the corollary. So they're exactly the same statement. So, but I'll still, I'm going to write them down. So this is the theorem. So theorem, I'm going to put theorem A. You take S between 1 and S between 0 and 1. You take P between 1 and infinity. Again, we're going to work in the entire space. So I take a function U in the homogeneous fractional Sobolev space WSP over N. And then what you can prove is that you can find a sequence of functions. Then there is a smooth functions UN, C infinity, with compact support, such that, and now we're going to use state of the gradient, you're going to have the semi-norms. So the semi-norms of UN minus U in WSP goes to 0. And so you have the same type. This is like, let me move it. I should not do this, but this is exactly the equivalent of the theorem of Eichelatz and Kalamarshkat for the fractional Sobolev case. So this is this. And then I'm going to give you two applications. So one is going to be the equivalent of the Gagliardo-Sober and Nigger embedding theorem. And the other one is going to be RD inequality. So I'll give you two corollaries of this theorem. So corollary 1, say corollary, say let's call it B. Let's do the subcritical case again. So let me take W. So I take S between 0 and 1, P between 1 and infinity, and we are doing the subcritical case. So let's assume that SP is less than N, so subcritical. You take a function in the homogeneous fractional Sobolev space, and then as before, you can find a constant. Then there is a constant which depends on the function Cu, such that the function U minus this constant belongs to the LP, the critical LP. So LP star S over N, and you can bound this by a constant times the semi-norms of U. And so again, so this is the, if you want, this is the Gagliardo Sobolev near, well, Gagliardo near, what's, I never know in which order, Gagliardo. So let's put Sobolev, oh, sorry. Sobolev Gagliardo Nirenberg. Nirenberg inequality. And P star, so the critical exponent, so this is the equivalent of the one for W1P, so it's NP divided by N minus SP. So this is the classical critical exponent. Okay, so this is one application. The other application, it's you could prove RD inequalities. So say corollary B, corollary C. So you have RD inequality. In this case, so you take again S between 0 and 1, P between 1 and infinity. You assume that SP is strictly less than 1, and you take a function in the homogeneous over space, but in the half space. So U, it's in W in the homogeneous SP, but only in the half space. So you are in this region here, Rn plus. And then what you can prove is that there is a constant. Then there is a constant, again, it depends on U, such that the integral over Rn plus of the function minus this constant raised to the power P divided by the last, the xn. The xn is the component of x in the last component to the power sp in the x. It's bounded by the seminorm. Probably, I don't know if I have. Okay. I don't know if I have power P here or not. I don't remember. Okay. Okay. So these are just two applications of this density result. Okay. Let's talk about now. Let me go back about theorem A. This is not a new result. So I'll tell you. So there's been work. There have been different proofs of this theorem, and so let me go. Let me talk a little bit about the literature and to explain what has been done about theorem A. So maybe I can. Let's see if I can do this. I'm gonna copy it. Okay, so the rest of the talk, I'm just gonna discuss about theorem A. I don't think I'll be able to give a proof, maybe just a little part of the proof at the end. But let me recopy the theorem. Okay, so now, yeah, I want to discuss what has been done about this theorem. Okay, so let's talk about previous results. So there was a proof in the subcritical case, so Mironescu, in 2018, so a relative recent paper. It's actually a beautiful review paper on Hardy inequalities and fractional solver spaces. So I really like this paper. So what he proved? So he proved proved theorem A in the subcritical case, in the case in which SP is strictly less than n. And the reason what he was trying, why he was interested in this space is he was trying to give different characterizations of the homogeneous solver space in the subcritical case. And so the theorem that Mironescu proved is the following. So Mironescu. He was considering the space you take again. Again, I have to say subcritical. So P between 1 and infinity as between 0 and 1, SP subcritical. So this is the main condition. And so he was consider the space of infinity function with compact support. And then you close it with respect to the fractional seminorm. So you consider the closure of this space with respect to WSP. And what he proved is that he gave several different characterizations of what this space is. And the first one, and it's related to the Sobel-Gallardo-Nierman inequality, he proved that this is equal to all the function u, which are in the critical in LP star, for which the fractional seminorm is finite. So this is one characterization. A second characterization of this space, this is all functions, say, LP lock. So function, say, I'm going to say measurable, for which essentially you have Rd inequality. So the integral over Rn of u to the power p divided by the norm of x to the sp in the x. This is finite. So this is the Rd inequality, but in the entire space, a version of Rd inequality. And then you also prove that this is also the same, the function u, I'm going to say measurable, for which when you take the limit of very large balls, so I take r goes to infinity, the integral of the ball center at 0 radius r of u in dx, this is equal to 0. And so in the subcritical case, he was able to prove that the closure of this function's infinity function with compact support with respect to the fractional semi-norm, in this case it's actually a norm, it's any of these three spaces. They're all the same. And so, and the key to prove this theorem was theorem A in the subcritical case. Okay, so this is one, if you want one more application of theorem A.
Can I ask a question there?
Of course.
So the first equivalent definition says that U is in WSP, but the second and the third, do they also require
that? Because I forgot. All of them are, yeah. That's a good question. U, WSP, yeah, so you need it in all of them.
So and that you can get the converse of the...
Yeah. All of them are in WSP. So these are all, is like essentially additional condition that you add to the homogeneous Sobel space to yeah. So all of them are like this.
Okay, thank you.
Yeah, no, thank you. Okay, so this is Mironescu. Then in 2021, so actually this is even more recent, there's a paper of so Brash, so 2021, so Brasco, then Gomez, so Gomez and Vasquez, Gomez Castro. It's I'm doing a poor job there. This is the same person. I don't know to Castro. So this is one name, and then and Vasquez. So this is the paper just came out. So 2021. What they did, they proved theorem A in the subcritical case, so SP less than n. In the critical case, SP equal n, and they proved a weaker version in the supercritical, and so weaker version when SP is bigger than n. Weaker version, I means that instead of proving, let me go, this is in an error, like instead of proving that they prove that there's a sequence of infinite function with compact support, such that when I do un minus u, instead of going to 0, this is just bounded. Okay, so in the subcritical, in this case, they prove that un minus u in WSP, the sup in n, it's finite. So it doesn't go to 0, but it's finite. And the Miroeshko's proof uses the fact that you are subcritical, and the paper of Brashko, Gomez, and Castro and Vasquez, they give 3 different proofs depending on the subcritical, subcritical, critical, and supercritical. So there are essentially 3 proofs of theorem A, depending on in which critical case you are. And as an application of, once they prove this theorem and also the weaker version in the they are able to give again a similar type of characterization of the spaces, slightly different type of spaces. So theorem, so this is Brashko, Gomez, Castro, and Vasquez. And so the theorem that they prove is that if you are subcritical, they consider, so it's slightly different from what Miroeshko is doing. You take, let me call it, say, DSP over n. So you take all Cauchy sequences. So like this is the quotient space of all Cauchy sequences in the space infinity with compact support, and Cauchy with respect to the fractional semi-norm. And so it's like essentially it's, I mean, this is like complicated to say, if you have a space which is not complete, the standard way to complete it is to just take all the Cauchy sequence, you define an equivalence relations, and then you take the quotient space with respect to this equivalent correlation. So this is the completion of the space infinity with compact support with respect to WSP. And so what they were able to prove is that they have 3 results. In the case, subcritical case, that they were able to prove that this space, it's equivalent to this one. So the space of functions which are in LP star. So this so in the subcritical case, this is just the function which are in the LP stars in the critical exponent, and they find a semi-norm. In the critical case, they proved that this quotient space, it's equivalent to functions which are in BMO. So bounded mean oscillation is finite, and you have the fractional semi-norm always finite, of course. But you have to quotient this space with respect to constant. So these are like equivalence classes when 2 functions are equivalent if the difference differs by a constant. So u equivalent to v if u minus v is equal to a constant. And then in the supercritical case, they prove that this space can be identified with functions which are Holder continuous, and they find finite fractional semi-norm. So u in C0 alpha, and the semi-norm is finite. And again, you quotient out, you do the quotient with respect to, you mod out constant. So you use this equivalent relation. And alpha, it's the standard one for the embedding. So So alpha, it's S minus N over P. Okay, so these are the result. This is what they were able to prove. And again, as I said, they used theorem A. And so now what I want to do is like, it's to give you a very quick sketch of a proof. So the idea, like, to give a proof of theorem A, which works for all three cases. And so you don't have to give three different proofs, like in the cases subcritical, critical, supercritical. But I just want to give one proof, the same proof, which works in all three cases. And I think it's relatively simple. And so, so now let me maybe copy again theorem A, if I can find it. Yeah, okay.
Can I ask a question?
Sure.
So I actually don't get the result. Could you go up plus or more? And actually, weaker version theorem, I don't get the meaning, because if one take UN equal to 0, it satisfies. So maybe I'm
I'm being a bit sloppy here. Yeah. It's like, yeah, let's put oops. Yeah,
okay.
they are able. It's I would have to write down, like, I have to tell you what the sequence is.
Okay.
And then it will make sense. Yeah, but
okay,
yeah. So I'm being sloppy. Yeah, I agree.
Okay, thank you.
Yeah. And I'll explain when I get to the proof. I'll tell you what the sequence that they constructed is, and so then you'll understand what I mean with weaker version.
Okay, thank you.
Yeah, you're welcome. Okay, so do I still have it? No, I lost it. Okay, so let me give you a proof. Okay, no, I'm not saying proof. Sketch or proof. Of theorem A. I'm going to need a lemma, which is actually not a lemma. I'm going to use Poincare inequality, so I'm going to write it down. Poincare inequality. So you take in fractional subspace. So you take a bounded set, so omega in Rn open bounded. You take P between 1 and infinity, and you take S between 0 and 1. And then you take any subset, so you take a subset E of omega. This I'm going to take Lebesgue measurable, and say with positive measure. And then what you can prove is that then if I do the integral over omega of U minus the average over the set E of U raised to the power P in dx, this is bounded by a constant. The diameter of the function, so the diameter of the set, so the diameter of omega, here this is important, n plus sp, divided by the Lebesgue measure of the set E, and then you have the semi-norm raised to the power P, W as P of omega. There. And this is true for every U in WSP. If I have time, I'll give you the proof. This is actually, it's much simpler than the one for regular solver spaces. This is a simple proof. It's just using more or less Minkowski inequality for integrals and not much else. Okay, but so we're going to use Poincare inequality. Okay, so let me start. Let me give you, tell you what's the idea of the proof. So let me now sketch of the proof of theorem A. So you take, so you start with the function which is in WSP, the homogeneous space, and you can use, if you use modifiers, you can also assume that U is in infinity. This is not a problem. Essentially, so what you want to do, you want to truncate this function. So you want to construct a sequence of functions which are infinity with compact support. So you want to approximate U, well, not really U, but say U minus a constant with a function with compact support. And so then you do, I mean, you don't have much else. You start by a cutoff function, right? So you take a function phi, which is infinity with compact support in Rn. And phi, you're going to take it to be 1 on the unit ball. So phi is equal to 1 in the ball center at 0 and radius 1. And it's 0 outside of the ball of radius 2. So phi is equal to 0 if, so in Rn minus the ball center at 0 and radius 2. And then you scale the function phi, so you want larger and larger balls, right? Because you want the function, you're trying to approximate U, and so you need phi n, which is just phi of x divided by n. And so what this does, this is going to be phi n. It's going to be 1 in the ball of radius 0 and center at 0 and radius n. So this sequence is getting larger and larger, and is approaching 1 everywhere. Okay, and then the idea, so the idea is that, okay, you want to take phi n, and in theory you would like to take U, but U is not going to work. Okay, so if you try, this is not going to work, and so then you have to take U minus a constant, and so a constant Cn. And so you got, coming back to your question, this is the sequence that the sequence UN. This is the one that they proved that they were able to find the constant Cn for which this sequence is bounded. This is what I meant over there by when I said, so when there's a sloppy version, this is the correct version of the result. And so the constant, so the constant, which is definitely in Mironesco's paper, and it's in the proof 1, I don't remember, in the subcritical case, maybe 1 and 3, I don't remember exactly. So say Mironesco for sure. The constant that it took was the average over a large ball. Okay, and also in Brasco, Castro and Vasquez, again, was something like this, average in large balls. What I did, the only change that I did, instead of taking this, but then the proof becomes completely different. Instead of working with balls, work with annualized. Okay, so you take, so let's take as a sequence Cn. Let me take, let's consider the annulus An. So you take the ball center at 0 radius 2n, and you subtract the ball center at 0 and radius n, and then you take as Cn the average over this annulus. Okay. And okay, so now I'm gonna try to explain why, so just you can make this change and then how to prove that, what happens with the proof. Okay, so what do you want to prove? So this is the sequence UN. So UN, it's phi n, u minus the average over the annual u. And so what you want, you're trying to prove that u minus un goes to 0 in the semi-norm. And okay, so I'm gonna add a constant. So this is a semi-norm, so you don't see constant. So I do u minus the average of an minus un. I'm gonna rewrite un. This is phi n u minus its average. Semi-norm. And so this I can rewrite. So this is the same as 1 minus phi n. And then I have u minus the average over the annulus. Okay. I'm going to call this function Vn. And so we want to prove, so to finish, we want to prove that Vn, the semi-norms of Vn goes to 0. Okay, so the way you do it, and this is like usually this is standard proofs whenever you work with fractional solver space, you take down the definition of the semi-norms and you just break it into a bunch of sets. And there's nothing fancy. So this is all the proofs are all like this. Break down in number of sets, and then you want to estimate each of the sets. And so let me write down, so Vn raised to the power p, WSP. And so, okay, and the semi-norms is symmetric, so x and y are very symmetric. So you can interchange x with y. And so what you do is like you break it down. Okay, there's going to be 2. In some of them you have some 2. So you're going to have the integral. Let me start over the ball outside. And so this integral, I'm not going to write down the function, what I put inside. So you have the integral over the ball and the integral over the ball. And then, yes, the semi-norm. Okay, so whatever you have inside. Then you have the integral over the ball and then the integral over the annuli, an. This is the annulus ball p center at 0 reduced to n minus center at 0 reduced to n. Then you have the twice the integral over the ball, the complement of the ball, so Rn minus the ball center at 0 reduced to n. And so here you took care of all the parts where you have the ball outside. Then you have the integral over the annulus, so annulus. And then you have the annulus and the complement of the ball, Rn minus the ball center at 0 reduced to n. And then the last one, it's the complement of the ball center at 0 reduced to n, complement of the ball center at 0 and reduced to n. And so you have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6 terms, and you just estimate each one of them. Okay, so this is the first one. Remember, phi n was 1 on the unit ball, on the ball of radius n. So this one drops out because phi n, so 1 minus phi n is equal to 0 in the ball center at 0 radius n. So the first one drops out. And then how much time do I have? You're muted.
As I tell everyone else, I'm here until you're done talking. So
No,
10 more minutes is okay.
Yeah, oh, that's perfect. Yeah.
Right.
I'm just gonna, so what I'll do, so like, let's say the first one, I'm just gonna maybe explain one term, like this one. And then all the other ones are similar, like it's the same type of proofs that you use. And so let me explain these terms here. And let's call, maybe I'll call, so this was 1, let me call this 2. And so let's estimate 2. And so 2, I'm gonna drop well, okay. 2 is the integral of the ball. And then you have the integral over the annulus. And then, okay, so now let me write down the semi-norm. So this is Vn of y minus Vn of x power p divided by the norm of x minus y and plus sp in dx in dy. Now remember what I said. The function, so Vn, this is 0 because y is in the ball and 1 so phi n, 1 minus phi n is equal to 0. So here you don't have this. So this one is actually, it's twice the integral of the ball, the integral of the annulus. It's the 1 minus phi n at x, and then you have the function u of x minus the average over the annulus raised to the power p x minus y and plus sp dx dy. Okay. Okay, so then you take, let's take this function. So I have, and I'm gonna call it, let me call it, say, psi n of x to be 1 minus phi n. And then I take, okay, so we know that psi n of x, I'm gonna rewrite it, this is psi n of x minus, at the point y, so if I take this y is in the ball, the function phi n was 1 on the ball, so psi n of y, this is 0. I use the mean value theorem. And so you get the gradient of psi n at some point z in a product x minus y. And the gradient, if you remember, phi n of x was phi of x over n. So when you do the gradient, you pick up, so this is 1 over n, the gradient of phi computed at x over n, so z in a product with x minus y. Okay, and so now I'm going to replace this term here, 1 minus phi x, with this expression here. Okay, so this, okay, so all of this is just, this is not part of the equality, so this is separate. So I go back, so this is 2, the integral of the ball. So you have 1 over n, so let me, maybe I put stuff outside. And let me be sloppy, so I put more or less. So I have, there's 1 over n raised to the power p. So you get 1 over n to the power p. Then you have the gradient of phi. This is just a constant, so I'll just put gradient of phi in L infinity raised to the power p. And then what you're left, you have the integral over the ball, the integral over Rn. Then you have u of x minus the average over the annulus raised to the power p in dx, and then in dy, and then you have x minus y and plus sp. Okay.
Minus 1 in the bottom?
Where are you?
Because of the gradient of phi, you should...
Oh, minus p. minus
minus p.
Minus p. Yes. Yeah. Otherwise, we are in big trouble. Yeah.
Yeah.
Thank you. Yeah. So this is this bit here. Thank you. Minus p. So this comes. Okay. So then what do? You flip the integrals, and so okay. So I go up. So you have okay. I'm gonna drop all these constants. So this 1 over n to the p. I'll take the integral outside is the integral. Here I'm gonna use Poincaré in this one, of course. Again, power p in dx, and then the integral outside. Well, I should not put dx. Because I'm in this situation, I'm gonna go up. So this is less or equal. Less or equal, and there are a bunch of constant. Instead of putting the ball, so I'll put the integral over the ball, center at what do I want? Center at x, and radius 3n of 1 over x minus y and plus sp minus p, and I'm integrating in dy. Does it make sense? So I'm using the fact that x, so if I take, if y is in the annulus, then the distance from x to y, it's if y is in the ball, not in the annulus. The distance from x to y is, I just use the triangle inequality, is less than the norm of x plus the norm of y. The norm of x is less than n. The norm of y is less than 2n, because y is in the annulus, vice versa, 2n and n. And so you get 3n. Okay, so then this one you can solve. So you use polar coordinates. So this is 1 over n to the p integral over an u of x minus the average. I'm almost done. So you use polar coordinates. You get the integral from 0 to 3n. There's going to be some constant. You have r to the n minus 1 divided by r to the n plus sp minus p in dr. So when you these two cancel out, and so you should get and so it is 1 over np integral over n ux minus the average. So you're gonna get n to the, I'm very bad at doing integral, to the 1 minus sp. So you move this one up. So it's n 1 minus sp. So you cancel one of them. So this one cancel with the 1. And so you have 1 over n to the sp, the integral over in of ux minus its average. Then use Poincaré inequality. And when you use Poincaré, you're going to get the diameter of an, and I'm just going to put the diameter of it is going to be like 3 to the n, 2 to the n, and the diameter was raised to the power, let's look Poincaré. Poincaré n plus sp. So you get n plus sp. Then you have to take the measure of the set. The measure of the set again is roughly is going to be n, like okay, I'm being sloppy with the constant, n to the power n. And then you have the semi-norm. The semi-norm in of sp in the annulus an to the power p. And so what's happening is that all the constants are dropping out. this is cancelled with this, and this is cancelled with this. And so you're left with the semi-norm on the annulus, and the annulus is running away to infinity. So then you just apply the back-dominated convergence theorem, and this is going to 0. And so you're done. And so yeah, and that's it. So like the trick is that the annulus runs away to infinity. Then, I mean, this is term one. All the other ones are very similar. You always use this kind of tricks. Poincare is Poincare inequality and nothing else. So that's the only tool you use is just Poincare inequality. And so, as I said, the main advantage is that this proofs works. There's no restriction on critical, subcritical, or anything. It's all of them at the same time. And I'm done. Like, okay, I can stop here.
Wonderful. I see somebody in the chat had the same expression I did. Very nice.
Thank you.
This takes me back to the nice lectures that used to give at Carnegie Mellon, probably still give, but I'm not there for them now. So I'm very happy to hear this talk.
Yeah, thank you.
Let me open up to people in the audience. Are there questions?
I have a question.
Yes.
So there is a theory of a solverless space in metric spaces with measure, right? So can I extend the theory of a homogeneous solverless space in that setting and consider similar problem?
Probably because here, well, okay.
Because this proof looks very wide applicability and looks very simple. So if there are a proper setting, the proof should work, I think.
Yeah, so I'm thinking as long as you have Poincare, so like the one you're thinking like, yeah, source space in metric space is the one where you use the kind of super, like a different, like the function G you take. It depends, like Agelak, do you know the work of Agelak, Piotr? There are a bunch of people, yeah, maybe you could do it.
Yeah. I'm a little bit. Okay, thank you. Yeah.
Yeah, but yeah, so possibly yes, I think so. Yeah.
Thank you. Thank you.
Are there other questions?
Yeah, I can do that. I can make a file and post it and give it to you.
Are there other questions?
May I ask one?
Yeah.
When omega is the whole space, you have a more classical characterization of the fractional solverless space by the Fourier transform.
Yeah, you could use Little Lovewood Palais.
Yeah.
That's the one you're referring, the Little Lovewood Palais decomposition.
Yes.
Yeah, or you could use abstract interpolation.
Yes.
Yeah, okay, go ahead. Yep.
So in that case, do you have I mean, the result theorem A is known, is it?
That's a good question. I have not. I don't know. I've not seen it.
Oh, okay.
Which doesn't mean it doesn't exist. I've not seen it in the homogeneous, because like there, like when you use the little parallels, like it's easy to do the homogeneous case. You do the series which go from k from minus infinity all the way to plus infinity, right?
Yes.
I don't know. That's a good question.
Okay. Thank you.
I don't know. I'm thinking, yeah, if it's somewhere, it should be in one of the Tribbles books. There are 5 or 6, but they're hard to read. I don't know if Graphacus, no, for sure. And Triple,
okay.
no. I don't know if I've not seen it there.
Yes. In your in the range of your exponents, your definition of fractional solar space should coincide with that with a fractional solar space defined by Fourier transform.
Yeah, there is. Yeah. In the case, yeah, and yeah, they are exact. And even the in the homogeneous case, what you can prove is that, say, so if you have a tempered distribution, and so if I have a tempered distribution, and you assume that let me put a check to say this is the fractional semi. If the fractional semi-norm is finite, this is the one using Fourier transform. The little would play. Then what you can prove is that actually this is the this is given by a locally integrable function, so that you can find a function u which is an L1 log of Rn, such that t it's actually t of u. So it's like when you apply to a test function, the t of u applied to phi is just the integral of phi times u. And so this coincides with the definition I gave at the beginning. Yeah, so they are the same in that case. Yeah.
Oh, okay. Thank you.
Yeah.
Thank you very much.
Other questions?
May I have one more?
Sure.
Yes, my name is Takahashi from Osaka University. Thank you very much for your interesting talk. And I'm not familiar with the function space DSP, which appears in theorem of Blasco.
It was just it was just a notation.
Yes, DSPRN, is it different from the closure of the CC infinity Rn with respect to the seminorm?
They were taking.
Yes,
no, I mean
it's the quotient space of course.
Yeah, it was the quotient space. That's the other thing. Because they were taking. I mean, what they meant, you were taking equivalence classes of Cauchy sequence like this. Like no, not even. It was the closure of that space. So like, they were taking. So you would take. So the element. I use a different letter because the elements are this. They are equivalence classes of Cauchy sequences. But it is the closure of the CC infinity function with complete support. It is that.
Okay.
But in the sense of the closure, in the sense of metric spaces.
I see. And Blasco, Castro, and Vasquez also proved that SP called N case, and they characterize DSPRN when SP called N case. But how about the closure of CC infinity case? CC infinity Rn closured by the seminorm. Is there some characterization when SP called N case? I'm interested about the SP called N case because the Schrödinger-Moser inequality comes out.
Yeah, I understand. So you're saying this?
Yes, this is.
Yeah, so they prove that this is.
Yes, they characterize the DSPRN when SP called N case, but I'm interested in how about the characterization of the CC infinity Rn closure?
When you close this with respect to the seminorm.
Yes.
But I think you should be able to prove that it should be the same, right? So this.
I see.
Yeah, because like this is the closure. You should be able to identify this with this, so it should be the same. Yeah.
I see. So
up to constants, it should be the same.
Uh-huh.
Yeah.
Thank you very much.
So then, yes, you are in this space.
So the John Nielsen inequalities implies that the exponential integrability of the function
Yeah, you could.
in
Yeah.
WSP dot Rn when SP equal n. Huh?
Yeah.
I see. Thank you very much.
Are there further questions? I want to ask a question, so but I should still check to see if anybody else wants to ask a question first. So
I have.
Please, Yutaka.
Yeah. So in Blasco Gomez Castro Vasquez, if S is large, I think alpha is larger than 1.
Maybe I wrote it wrong. What's the I could be I screw up this point. What's the right? No, you want it has to be less than 1. So n. So maybe I just wrote the. It's the one it's the one for Morris inequality.
No, that should be right. S minus n over p. Because S is in 0, 1, right?
S is in 0, 1. Okay. Simply okay. So
this is less than, okay. Yeah. Sure. Okay.
Okay. Thank you. So, but can one consider S larger than 1 case?
In those, that's a good question. Nobody has done it.
Okay.
Yeah.
Okay.
So that.
Thank you.
Yeah. S bigger than 1. All these proofs are less than 1. I don't know.
Okay.
Yeah.
Yeah. In that case, one should factor out more than constant, but some polynomial.
Yeah. Polynomials.
Final order.
So it should be the equivalent, like this term in the for the fraction, for the non-fractional, the one, this is done, the Argelac paper, this is done for any k.
Okay.
But for the fractional, no. For the fractional, only s between 0 and 1.
Okay, thank you.
I've not seen s bigger than 1.
Okay, thank you.
Actually, I've not even seen, to be honest, I don't even know what Poincaré inequality. Yeah, I don't know.
Okay.
Yeah, I don't know.
Maybe one has to subtract not the constant but the polynomial.
Yeah, you have to subtract the polynomial.
Yeah. Thank you.
And probably here with polynomial you could do something like this.
Okay, thank you. Yeah.
Probably, yep.
So this slide right here, it's had me curious. When did you realize that you should try the instead of integration over the ball, it's integration over the annulus? And when did you realize that was actually going to work?
The annulus, Argelac, they are using also the annulus in the paper, in this paper. This one, but the proof, you cannot use their proof. So this paper, they are using also the annulus. And there's also the lecture note of Stefan Müller, in which is proving again regular Sobolev spaces, but is also using annulus instead of the. So the annulus is not new, like using the idea of the annulus. How that I was able to treat all of them, I was just curious to see, because when I read the paper, and they were, instead of the annulus, they were using the full ball, and I said, okay, let me try what happens with the annulus. And then there were all these parts, and it worked. I don't know. I was just curious to see if it was working or not.
But the moment that you realized it was going to go to 0, that was that
was nice. Yeah, because everything, it was canceling out when all the powers cancel out exactly. So, this is cute. So it's this like, because it's very sharp, like it's like, oh, so this is the right thing to do. Yeah, that was nice. Yeah, yeah.
Are there other questions? If not, then we'll thank the speaker again.